Kind invitation and warm hospitality. So this is about the quantum phase transition in string theory as well as from string theory. And I'd like first acknowledge these colleagues, especially the condensation experimentalist Philip Kim at Columbia University, and some of other string theorists. Shigeaki Sugimoto is, I think, somewhere in the audience. Okay, let me just go very quickly the introduction what the quantum phase transition is. The quantum phase transition is the following. If I have some quantum mechanical Hamiltonian with certain parameters which I will collectively call as G, this could be just finite degrees of freedom quantum system or infinite degrees of freedom the quantum field theory. As I dial or tune this coupling parameter G, at some point the quantum ground state undergoes the level crossing. This, if in that case, the ground state energy may develop some certain non-analyticity, and this non-analyticity is a clear sign of the phase transitions of second order, but now here without any temperature excitations, but in terms of this coupling parameters in quantum state. If this happens, we say it undergoes quantum phase transitions. At the same time, then the correlation length, as well as some time scale, as well as mass gap scale, associated with the ground state, may also have non-analytic changes across this coupling constant. Now, so one can think of the two questions which might be relevant for string theory. The first one is, can we have this quantum phase transition in string theory? This, I think, is an interesting question, and I will mention very briefly at the end just one comment that I'd like to comment and associate with the black hole and maybe also flux compactification. But for this talk, I'd like to ask another question, which is that can we find any quantum phase transition mimicked within the string theory? In other words, can we realize quantum phase transitions in condensed matter system, which is clearly realizable or concretely realizable within the string theory? Usually, this is very difficult. We already heard several talks today, and there are many noise or sometimes very difficult features of finite temperature or finite density systems, which is actually quite difficult to handle within the quantum field theory that we know of. Here, I'd like to bring you an attention to one very interesting development in condensed matter system for the last couple of years, which is associated with what is called the graphene. A graphene is the carbon monolayer, and if you have multi-layers fabricated in the laboratory, then I'd like to argue that it has nice parallel with certain D-brane configurations we are very familiar with. And in terms of that D-brane configuration, in fact, we can turn around and understand, at least hopefully understand, many features associated with graphene multi-layer dynamics. Why is it interesting? Because this system, as I will allude to you, has many variety of interesting phenomena, which we all have been asking in the quantum field theory. For example, dynamical mass generation, and the multi-flavor symmetry breaking, as well as parity symmetry breaking. And being the two-dimensional system, there's an issue of induced 2+1 Chern-Simons term, and as well as some supercritical instabilities. All these variety of the quantum field theory issues all come into this interesting condensed matter system. And that's what I want to bring you up. So what is the graphene? As I said, this is a monolayer of the carbons, and this is an example of what is called gap-ray semiconductor that condensed matter people have been always dreaming of, and it only recently has been able to fabricate in the laboratory. This is, in fact, very nice because sometimes the condensed matter colleagues do something good for you. It's not often, but in this case, they realize 2+1 dimensional 4-component direct fermions, rather than the dispersive fermions we always encounter in condensed matter systems. And because they are charged, their gauge interactions, for example, the electrodynamic interaction of these electrons and holes in this system, in the graphene multi-layers, have very interesting features, something we cannot do in QCD or in any other system. Namely, as I will briefly explain, by having different kinds of substrate on which this carbon monolayer is grown, I can actually tune and dial the coupling constant of these gauge interactions. So here we have a system, a condensed matter, where we can dial coupling constant as well as number of the 4-component direct fermions. And so there, I'd like to show that indeed there is a quantum phase transition we can study within the field theory and in the D-brane system, as well as from condensed matter experimental laboratories. And this string theory realization of the graphene quantum phase transition is, again, as I said, it's done in terms of the D-branes. I will explain how we do it. And we can study weak and strong coupling limit of this one, both in D-branes as well as in the laboratory. And I will explain how the string theory, D-brane configurations, tell us certain the qualitative features about the phase diagram at 0 temperature. And there's also the predictions at finite temperature, but pretty well I don't have any time to explain that further. And this is a very nice laboratory exploration of gauge gravity correspondence. And potentially, maybe we can test this all in the laboratory within a year or two, maybe before LHC turns up. What is graphene? Graphene is a carbon, so therefore it's black, you might think, but actually it's not true. This is the photograph of the graphene grown up on the substrate. Substrate is gold color here, and that's the base at 0 angstrom in height. And here is the graphene grown up in the half of the plate, and that is just 8 angstrom high. Okay? And there's another one here overlaid that is making the multi-layers. Okay, the graphene has this lattice structure of this type. Very simple. It's a hexagon. It's a lattice bonding on this, the tight binding on hexagon lattice structure. And this band structure is very elementary. Schrodinger equation exercise you can assign to your quantum mechanics course in undergraduate. In fact, this has been already done by Wallace many years ago. And in fact, if you compute this one and the low energy, then it has conduction band and the valence band meeting together at point, but the point is actually 2, not just 1. Furthermore, if you have a half filling, then this valence band and is completely filled, and you have basically realizing the direct C. And dispersion relation, dispersion relation is energy independent, meaning this is relativistic, and this has been pointed out many years ago, even in fact anticipated the Scanley semiconductor. And also in the laboratory, not you, but your colleague in condensed matter, actually can grow, as I said, heterogeneous multi-layer structures, which realizes the multi-flavors of the 2 plus 1 dimensional relativistic fermions. Okay, here's the cartoon view of the dispersion relation. As I said, this is the 2 plus 1 dimensional momentum space and the energy momentum space, and it is linear, therefore there's no dispersion there's no dispersion, and the Fermi velocity is the 1/300 of the speed of light, and it's a constant all over the Fermi surface. And I have feeling, as I said, this realizes direct vacuum, and the excitation on it are basically direct fermion. It's relativistic. And if I have an n multi-layer of this graphene, then we are having 2 plus 1 dimensional, the multi-flavors, and the symmetry of the fermions by themselves is U2n. Now, these are the 2-dimensional layers. If I just hand over the monolayer of graphene in air or maybe in vacuum, then they do interact by electromagnetic interactions. Then, of course, they are 3 plus 1 dimension interactions, even though the fermions are confined in 2-dimensional monolayers. And as I said, if I put some substrate of different dielectric constant, then I can change the fine structure constant, the namely strength of 3 plus 1 dimensional gauge interactions. And this is something we can do quite easily in the laboratory. So here's a cartoon view of the graphene suspended or hang in the substrate material. This the green color is substrate of 3-dimensional material, and on top, I just look at from the side, I have the multi-layers of graphenes. They are interacting, the photons in this substrate propagate through the 3 dimension, even though fermions are localized on 2 dimensions. As I said, the coupling constant, effective coupling constant of gauge interaction is not just E squared divided by dielectric constant. So if I change this substrate material, I'm tuning my coupling constant G. And also I can turn on the temperature, but I will restrict my talk on 0 temperature, the physics. So the D-brane setup of this one is the following. I start with N3 D3 branes. This is something everybody knows very well for many years from ADS-CFT days. Now I then introduce D7 branes along these directions, and notice that it just overlaps in 2 plus 1 dimension with D3 branes, and otherwise it's extended in the other directions. And I introduce N7 D7 branes, which in this case turned out to be even number. And then in these two systems have overall transverse direction, which is 9th in this notation. And then if I look at the D3, D7 interaction, the open string spectrum, then NS sector is completely massive. They don't have any massless mode. And Ramon sector, we have massless fermions. And these are precise the fermions that I talk about in the graphene system as multi-component 2 plus 1 dimensional fermions. So as usual, I will take N3 going to infinity limit, and tooth coupling is fixed, and N7, this 7 brane number is fixed. So this is quenched approximation. So this is set up I'm going to study, and the old spectrum here is exactly the same as the graphene multi-layer system interacting with the 3 plus 1 dimensional gauge interaction in the substrate. So this is again D-brane configuration cartoon. It's exactly the same shape as I drew. And here I only drew the 1, 2, 3 spatial plane. And if I look at first in the weak coupling side of this system, then there's something very interesting about it. First of all, remember that the D3 brane is a conformal field theory, N equals 4 super Young mill. Now it is now coupled to the massless 2 plus 1 dimensional direct fermions, and that's codimension 1 compared to the N equals 4 super Young mill. And therefore, for the most of the bulk, the conformal invariance, in fact the superconformal invariance, is never afflicted, and it's only the interaction between this 2 plus 1 dimensional fermion and 3 plus 1 of N equals super Young mill, which destroys the supersymmetry as well as conformal invariance. Okay, so if I were here to give a very simple elementary argument in terms of just a simple U1 gauge theory type argument, even though one can do a full non-abelian thing. So I have just a usual gauge interaction in 3 dimensions. It interacts with the graphene or this D7 brane fermions at the codimension 1 here x3 equals 0 side, and that's the usual fermion and it's the gauge interactions. Our study is multi-flavor, where psi is the even number of fermions. I suppress the flavor numbers. Then I study this system by iterating over the gauge field as well as the quantum loop effects. And here, in particular, our study in this multi-flavor systems, parity and flavor symmetry breaking patterns, and a dynamical mass generations as a signature of a quantum phase transition. Good. Suppose I first integrate, this is in 4-dimensional, 3 plus 1 dimensional photon dynamics. Suppose I just integrate out this x3 directional gauge interactions and rewrite everything in terms of 2 plus 1 dimensional field theory. So what do I get? This is the effective Lagrangian. Effective Lagrangian is completely novel in the sense that it has a kinetic term of the gauge field with a kernel of this type, and also this, I'm sorry, I forgot to mention this one. This is the gauge fixing term where C is the gauge fixing parameter. If I just integrate them as a gauge fixed Lagrangian, then I get also this kind of terms, and on top of that I have a usual 2 plus 1 dimensional fermion. So what is special about this Lagrangian? As I alluded, there is a very important constraint coming from the conformal invariance of underlying 3 plus 1 dimensional N equals 4 super Young mills. That is conformal invariant, and the graphene 2 plus 1 dimensional fermion would never afflict that symmetry. So it will be there, and that the conformal symmetry in 3 plus 1 dimension dictates that in 2 plus 1 dimensional effective Lagrangian kinetic term and gauge fixing term has to be solved. And here G is 3 plus 1 dimensional N equals 4 super Young mill coupling constant, which is dimensionless. So this whole system, the reason why it looks so funny and novel is because it just reflects the underlying 3 plus 1 dimensional conformal invariance. There is no dimension full coupling parameter in this theory. So compared to standard 2 plus 1 dimensional quantum field theory, this one has no coupling parameter, and therefore this defines a novel new 2 plus 1 dimensional conformal field theory. It's coupled to these fermions. Being so, if anything, any dimension full parameter is dynamically generated through the transmutation, then it has to be proportional to the UV cutoff scale, because there is no coupling constant, which carries a dimension, mass dimension. So therefore, in this system, when you look at the dynamical symmetry breaking associated with mass generation, then I have to first introduce UV cutoff, and then start the UV cutoff dependence, and eventually take the continuum limit. Even though this is conformal field theory, that's the fact of life, and we have to do it. Okay, so we will do all this one both in the weak coupling as well as in the strong coupling. First, the pattern of a flavor symmetry breaking as well as a parity. In this system, as I alluded, there is a flavor symmetry because I have for every graphene monolayer, I have two flavor fermion. If I have Ng, many of them, then I have a U to the 2G flavor symmetry. And then also on top of that, as an effective 2 plus 1 dimensional field theory viewpoint, I have a parity symmetry, which is basically flipping one of the spatial coordinates. And also at the same time, I can the exchange pairwise the flavors, and this I can define as a generalized 2 plus 1 dimensional parity. So this whole system has the flavor as well as a parity symmetry. Now, some time ago, Baffa and Witten argued, just based on mass inequality, that in 2 plus 1 dimension, U to the 2G flavor symmetry is broken to U to the Ng times U to the Ng. In other words, flavor symmetry is maximally broken, yet parity is unbroken. Okay? And this was based on the fermion determinant and the limit of the mass taken to 0. Here, I'd like to argue that it can be very elementary, in a very elementary way, understood in geometric the setup. So how do I do that? At the weak coupling limit, I have this D3 brane, and then I have the D7 branes on top of it, and now I'm drawing here only in the subspace where this is the one of the directions in the horizontal direction is overall transverse to D3 and D7. So if I look at this one, then I have to put the massless graphene, the fermion means that D3 and D7 are on top of each other, such that the open string between them is massless. So how do I do that? Geometrically, I have to put on this one, but that's ambiguous. I have to define what I mean by left and right more carefully. So the correct way of doing it is that I start with, let's say, one side and take the limit distance between D3 and D7, arbitrarily small, and to 0. And this is a geometric realization of the argument given by these people long time ago in the mass inequality. So I do that. When I do this one, then as much as well known in deep brain physics, this gives rise to Z2 charge fractionization, and then I have to also define what I mean by the vacuum in terms of left and right field, which means that I have to define what I mean by the Ramon-Lamont flux between left and right of these 7 branes. So if I do that all the correct in a precise and correct way, then the minimum energy configuration associated with the Ramon-Lamont field strength energy is such that I have equal numbers of D7 brane on the left of D3 and equal numbers of D7 on the right, such that the Ramon-Lamont field is confined only in the region between, and outside is completely 0. Otherwise, you have Ramon-Lamont field everywhere, and that energy is infinitely larger. Okay, then I do a standard field theory analysis. First, Schwinger-Dyson equation, solving the mass gap. And then I find well, I will skip the technical details. You can do it. And the only novelty is that here the gauge interaction is very different from standard 2 plus 1 dimensional field theory. If I do it, then the mass gap as a function of the energy scale or momentum scale P square takes this form. In other words, it has to be the effective coupling parameter has to be larger than certain value, which is dictated by this combination. And if it is so in a strong coupling region, then within this rainbow and approximation, it shows this characteristic pattern, namely, it goes like 1 over square root of momentum P times sine oscillation functions of log of momentum P. I invite you to remember this in just 10 minutes, then I want to compare with the strong coupling analysis. Now, as somebody who studied this one will already recall very well that this dynamical mass generation has to do with intuitive picture of supercritical instability of the fermion system when it's interacting with the gauge field. And the mass generation here also shows that it's really IR effect. In other words, it's picking up in the IR regions. And because of this instability of supercritical instability is set on, then the generation of mass is just to screen it. This is the physics. And therefore, what we can say from this one is that from at weak coupling side, if mass is dynamically generated, then we have a metal insulator with the quantum phase transitions in the space of coupling constant as well as the number of these graphene or D7 brane numbers. So this is the characteristic view of the phase diagram at zero temperature in the two dimension. One is the gauge coupling constant. This is D7 or the graphene, the multi-layer numbers. And at the weak coupling side, in the weak coupling side there is in the strong coupling side there is the gapless phase, and in this side there's a mass gap generated, and this crossing is basically metal insulator phase transitions. Okay, a vector fit equation, you can do it, and you get the consistent answer again. And there's also Goldstone boson you can find, which lives on this Grassmann. Strong coupling side, story is simple, as we all are familiar with, that we just replace by this D3 brane by the supergravity background. And then on that, I study probe D7 brane in the quenched approximation, or one can even extend it to the partially quenched ones. And the ground state configuration of D7 brane profile can be studied. In particular, I look at the profile of X9, which is the overall transverse direction of the D7 branes. And the reason is because this one is coupling to the fermions in this way. Therefore, it is basically a holographic dual to the mass term. Okay, good. For strong coupling effect, the first thing is that remember that we have the conformal field theory novel type. Therefore, the UV cutoff has to be introduced from the beginning at the outset. That means in the gravity side, ADS5 supergravity approximation is not enough because one has to introduce UV cutoff. And the way we do it is in terms of the D-brane supergravity background is that I introduce 10-dimensional flat background outside. So in other words, I look at the full geometry of D3 branes. So if I look at the D-brane minimum energy contribution from DBI analysis, at the weak coupling, as I showed, it's just straight line, not seeing anything. But at the strong coupling, it just bends. This is simple reflection of the fact that D0, D6 repair with each other. And actually, there's more of the features in between in the region of the ADS throat. And that's what I'm going to show now, momentarily. And in the flavor parity symmetry breaking is, again, is exactly in terms of this banded D7 branes and has exactly the same feature as weak coupling side. So symmetry breaking pattern is unchanged, exactly the same. And we can do also partial quenched up the structure. Now if I look at the detailed geometric profile of the D7 brane, then it has the following form. This is X9, which is a holographic dual to psi by psi, and that has a profile as a radial coordinate R is varied in this pattern. And this is exactly the same as the Schwinger-Dyson analysis at the weak coupling. The functional form is exactly the same, except that here the coupling dependence is completely fixed by dBi equation of motion. That's it. And this is remarkably the same as the weak coupling side. And there must be some deep truth in the weak coupling Schwinger-Dyson approximation, which we made earlier. And also at this very small r near the center of the ADS, X9 remains stable, which means what I mean by that is that even if I vary a boundary condition at infinity, it does not really change much. So order of only one change. And furthermore, if I go beyond the ADS rod, then D3 brane geometry deviates from this oscillatory supercritical instability and simply goes as one of our the cube behavior, and that's very easy to understand intuitively because this is like an inserting psi by psi source which is coupling to the X9 in minimal way. So from the strong coupling analysis based on supergravity, we found that D-brane setup basically realizes the conformal quantum phase transition based on conformal field theory, and it gives rise to flavor and parity symmetry breaking pattern as we understood at the weak coupling side, but in more geometric pattern. And dynamical mass is generated in the region inside the ADS, but way above from the center, but way inside the ADS slot. And we have also given the geometric interpretation of supercritical instability, and this also we extended quite straightforwardly to the partially quenched fermion cases. And this may be tested against the lattice simulations. So string prediction of the phase diagram is slightly different. Basically, the termination point in the number of N7, which is the D7 brane, is not there because we are within the DB analysis. We don't see any changes in the profile as N7 is varied even from 1 to infinity. Of course, when N7 is very large, order of N3, then there's large bag reaction. Therefore, DB analysis is inapplicable. So there's a certain room here that we don't understand yet, and that requires a full bag reactions. Non-analyticity of the mass, dynamic general mass, we expect that, from the supergrid analysis, we expect this red line, which means that it's a non-analytic at critical couplings of tube coupling, but still the further analysis needs to be done because this is only leading order result. We actually have several occasions that this non-analytic behavior smoothens out by supergravity fluctuation corrections. Okay, there are many other results, finite temperature and other dimensions, but there is very different. And also the compactified Z direction, the D3 brane, the extra direction such that it actually has the three-dimensional, the mass scale, the cutoff scale, much like these people have already suggested a long time ago. And also some transport properties. And also one can also consider odd numbers of the fermions, 2 plus 1 fermions, by deforming, actually by hand, we can deform graphene multilayer, and that just lift up the Fermi surface and open the gap. And you can actually have that system and odd numbers of fermion flavors. And in that case, there's a parity symmetry breaking always, and induced Chern-Simon term effect can be studied. So conclusion, you can read from this one. I'm running out of time. I just want to mention one thing. As I said, there's another, the quantum phase we can contemplate of in string theory, which is that if I have the flux or black hole, flux compactification of black holes, then those systems may have quantum phase transition as I dial certain parameters in defining those systems. So one example I'm currently studying is decay of the quarter BPS state, which already we heard from Sen and Moore. Okay, so I just want to finish my talk. This is my conclusion. Many years ago when I was at Santa Barbara, I happened to sit in between two great practitioners of wave functions. And the Bob Lofgren said, I found an incredibly beautiful wave function strong interacting many electrons in semiconductor. Then Hato, a man of great wit, just replied, some time ago I found the wave function of the universe. Isn't yours a tiny part of mine? So we are theorists of everything. Thank you.
David?
That was a lot of nice stuff, but on the three-dimensional, at the level of the three-dimensional field theory where you did some rainbow graphs, there you have a conformally invariant but non-local 2 plus 1 dimensional theory, right?
That's right, exactly. So
in such a theory, don't you have a priori an infinite number of dimension 3 operators? Since you have non-local, I mean,
well, the gauge.
How do you control such a theory? There's an infinite number of dimensionless couplings.
Okay, that may well be able to. I just use the propagator, which is 1 over p and 1 over p square in the Schwinger-Dyson analysis. The coefficient might be changed, but I don't see any other tensorial structure which is permitted by the gauge invariance. That's all I have.
You allow inverse derivatives, you can do...
But I guess the gauge invariance and the Lorentz invariance constraints are a lot of them.
I don't think so.
Any further question or comment?
Here.
Yes,
Yeah.
David.
So my question is related to David's actually. So maybe I missed the point, but you were trying to describe a real system where you have fermions in 2 plus 1 dimensions interacting through a 3 plus 1 dimensional abelian gauge field, if I understood correctly, electromagnetic gauge field.
Right.
But what you get in ADS-CFT is 2 plus 1 dimensional fermions interacting through a 4-dimensional non-abelian.
Very good. But they share the same.
So how?
Okay, I understand your question. My answer is that they share the same physics. Namely, there's a conformal invariance. The only way we get the conformal invariant, the 3 plus 1 dimensional setup out of D brane is n equal to super Yang-Mills. As a field theory, we can have many different things. But as a D-brane setup, so n equal to super Yang-Mills is the only way I can get conformal invariant interactions.
Yeah, you get n equals 4 super Yang-Mills, but that's an abelian interaction. So how do you go from that to the system you want to model?
Okay, but the system,
an abelian interaction.
Both of them are governed by the conformal invariance, the interactions. So the coupling constant in the graphene is the electromagnetic interaction, and in the D-brane setup is the 't Hooft coupling. They are genuine coupling parameter, and you can dial, not running parameters.
Well, before we thank our speaker again, remember that you have to be on time at 8:30 at the restaurant. Okay? Let's thank our speaker.